1a, define velocity. Velocity equal to change in displacement divided by time taken. B, the drag force Fd acting on a car moving with the speed v along a straight horizontal road is given by Fd equals v squared a k, where k is a constant and a is the cross-sectional area of the car, determined as SI base unit of k. So equation given Fd v squared a k, we want to determine the SI base unit of k. So k equal to Fd v squared a. Fd is the drag force. Base unit of force is kg and s negative 2. Unit for speed m s negative 1 and unit of area is n squared. So now become kg m s negative 2 m squared s negative 2 m squared. So kg m negative 3. C, the value of k in SI base unit of the car in B is 0.24. So this is the k value. The cross-sectional area of the car is 5.1 meter squared. This is the area. The car is travelling with a constant speed along a straight road, and the output power of the engine is 4.8 10 power of 4 watt. This is power. Assuming that the output power of the engine is equal to the rate at which the drag force Fd is doing work against the car, determine the speed of the car. So determine speed. So formula, power equal to Fv. Force just now is V squared AKB, power. So we have V cube A, V power of 3 AK, power. So power given 4.8 10 power 4. We want to calculate V power of 3, area 5.1 and value of K 0.24. So speed equal to 33.71, 34.0 meter per second. 2A, figure 2.1 shows the velocity time graph for an object moving in a straight line. 1. Determine an expression in terms of V, U, and T for the area under the graph. So area under the graph. Okay, this is the trapezium. So area under the graph, A equal to half U plus V, time taken. So half U plus V T. A2, state the name of the quantity represented by the area under the graph. This is the graph velocity time graph. Area under the graph is displacement. To B, a ball is kicked with a velocity of 50 meter per second at angle of 60 degree to the horizontal ground. So this is B, this is the angle. The ball then strikes a vertical wall at the instant when the path of the ball becomes horizontal as shown in figure 2.2. Assume that air resistance is negligible. Okay, this is the projectile motion. So you have to resolve the y component and x component. So this is x component. Horizontal velocity is u cos theta. And y component, vertical component, become u sine theta. One, by considering the vertical motion of the ball, calculate the time taken to reach the wall. Calculate time taken, calculate t. Okay. So when the ball reach the wall, look something like this. This is wall and then ball. Ball reach the wall. So when the ball reach the wall, here at maximum height. So we know that at maximum height, Vy equal to 0. Calculate time taken. V equals to U plus AT. Vertical motion, Y component, Y component, Y component. Vy at maximum height is 0. Uy, U sine theta. Object going upward, negative G time taken. So 0, 15, sine 60, negative 9.81 t. T equal to 1.32 seconds. 2. Explain why the horizontal component of the velocity of the ball remains constant as it moves to the wall. So we know that horizontal component not affected by gravitational force. So we can say that the force in the horizontal direction is 0. P3, show that the ball strikes the wall with a horizontal velocity of 7.5 meter per second. Horizontal velocity Vx equals to U cos theta, 15 cos 60 degree. So we have 7.5 meter per second. To see the mass of the ball in B is 0.4 kilogram. It is in contact with the wall for a time of 0.12 seconds and rebounds horizontally with a speed of 4.3 meter per second. 1. Use the information of B3. Okay, B3 horizontal is 7.5 meter per second. Calculate the change in momentum of the ball due to collision. Okay, so ball initially u 7.5 meter per second, then after that rebounds B with the speed 4.3 meter per second, but because the rebound in the opposite direction, so here become negative. Okay, now time taken is 0.12 seconds. Okay, calculate change in momentum. So momentum equal to mv minus mu, mass 0.4 kilogram, speed, final velocity negative 4.3 minus inertial 7.5. We have 4.72. C2, calculate the magnitude of the average force exerted on the ball by the wall. So force equal to rate change of momentum. Change in momentum 4.72, time taken 0.12 seconds. So we have 39.3 Newton. 39.3 Newton. Explain what is meant by work done. Work done is force times distance in direction of force. 3b, a ball of mass 0.42 kilogram, this is mass, is dropped from the top of a building. The ball falls from rest, so U equal to 0, through a vertical distance of 78 meters to the ground. So this is SY. Air resistance is significant so that the ball reaches constant terminal velocity before hitting the ground. The ball hits the ground with a speed of 23 meters per second. This is V. 1. Calculate the ball falling from the top of the building to the ground. Decrease in gravitational potential energy. So, decrease in gravitational potential energy. MGH, mass 0.42, G value 9.81, and height 78 meters. So, decrease in gravitational potential energy 321 joule. 2. The increase in kinetic energy. So, when the ball decrease in gravitational potential energy, so ball gain kinetic energy. So, we want to calculate kinetic energy. Kinetic energy is half mv squared, half mass 0.42, and then speed 23 meters per second. So we have 111 joule. 2. Use your answer in B2 to determine the average resistive force acting on the ball as it falls from the top of the building to the ground. Okay, so we know that gravitational potential energy of the ball 321 joule and kinetic energy equal to 111 joule. So kinetic energy is not equal with the gravitational potential energy. Some energy is lost due to the resistive force. Okay, now we want to calculate resistive force. So there is a difference between gravitational potential energy and potential energy. So work done equal to force times distance. 321 joule minus 111 joule equal to force distance 78 meter. So force equal to 2.69 Newton. 3C, the ball in B is dropped at time t equal to 0 and hits the ground at time t equal to t. The acceleration of the free fall is g. On figure 3.1, sketch a line to show the variation of the acceleration A of the ball with time t from time t equal to 0 to t equal to t. Okay, so starting point, t at t equal to 0. When the ball at maximum height, this is ball, only weight pointing downward. So for here, we said that acceleration equal with the gravitational acceleration 9.81 ms negative 2. So at the time t, air resistance start to increase, but weight pointing downward constant. So for here, we said that acceleration less than gravitational acceleration. So when the ball hit the ground or when the air resistance equal with the weight, so here we said that achieve terminal velocity. So acceleration equal to 0. But we must remember that here, air resistance is significant so that the ball reach the constant terminal speed before hit the ground. So meaning the ball reach the ground before t. Okay, ball reach the ground before t. So first acceleration is g, then after that acceleration start to decrease, then after that acceleration 0 before t. So we said that until here lah. So acceleration decreasing due to the air resistance. So we can draw graph like this. Okay. For A, state the difference between progressive wave and stationary wave in terms of the transfer of energy along the wave. So progressive wave transfer energy and stationary wave do not transfer energy. For B, a progressive wave travels from left to right along a stretched string. Figure 4.1 shows part of the string at one instant. P, Q, and R are the three different points on the string. The distance between P and R is 0.48 meters. The wave has a period of 0.020 seconds. So this is the period, capital T. 1. Use figure 4.1 to determine the wavelength of the wave. Okay. So given distance P to R is 0.48 meter. Okay, how many wavelength from P to R? So P until here, one wavelength. And then from here to R, another half wavelength. So from P to R is 1.5 wavelength. 1.5 wavelength equal to 3/2 wavelength equal 0.48 meter. So wavelength equal to 0.32 meter. To calculate speed of the wave. Speed equal to frequency times wavelength. Frequency is 1/time taken wavelength. Time taken given 0.020 second and wavelength 0.32 meter. So we have speed 16 meter per second. B3, determine the phase difference between point Q and R. Okay, so where is point Q and R? Okay, point Q and R. This is point Q, this is point R. Okay, how many wavelength Q to R? Until here, one wavelength. And then from this point to R is another quarter wavelength. So Q to R equal to 1 plus quarter wavelength equal to 5/4 wavelength. So 1 wavelength equal to 360 degree. So 5/4 wavelength equal to 5/4 times 360 degree equal to 450 degrees. So phase difference between point Q and R is 450 degree. Before, figure 4.1 shows the position of the string at time t equal to 0. Describe how the displacement of point Q on the string varies with time from t equal to 0 to t equal 0.010 second. Okay, so we know that period equal to 0.020 second. So if we want to calculate or identify t at instant time, so we have divide by 4 equal to 0.005 second. So 0.005 second is the time at instant time. So at t equal to 0, this is position of Q. Okay, this is Q. Then after that here, at T1, 0.005 second, this is point Q. And then here at T2, at 0.01 second, Q move to at equilibrium. Okay, so we can say that at T equal to 0.005 second, Q has maximum displacement. Okay, maximum displacement downward. Downward maximum displacement. And then when the T equal to 0.01 second, Q returns to original point or position. For C, a stationary wave is formed on different string that is stretched between two fixed points X and Y. Figure 4.2 shows the position of the string when each point is at its maximum displacement. 1. Explain what is meant by a node of a stationary wave. So node is 0 amplitude, or we can say 0 motion. State the number of antinodes of the wave shown in figure 4.2. So X here is node, then antinode, here node, antinode, node. So the number of antinodes, 1, 2. So we have 2. State the phase difference between point X and Z on the string. Okay, so what is the phase difference of stationary wave? So phase difference in stationary wave between two particles is equal to the n wavelength. N is the number of nodes between the two particles. So because W and Z has one node only, okay, here only we have one node only, so one wavelength equal to 180 degree. C4, a new stationary wave is now formed on the string. The new wave has a frequency that is half of the frequency of the wave shown in figure 5.2. The speed of the wave is unchanged. On figure 5.3, draw a position of the string for this new wave when each point is at its maximum displacement. Okay, so we have V equal to F wavelength, and then frequency equal to V over wavelength. So we know that frequency become half. So here frequency is half, speed is not unchanged, so meaning the wavelength become 2 times. So how the string looks like? So wavelength become 2 times. So here become like this. So this is node, antinode, and node. Number 5, one end of wire is attached to a fixed point. A force F is applied to the wire to cause extension X. The variation with F of X is shown in figure 4.1. So from figure 4.1, we have graph straight line pass to origin, extension again, force. So the idea here, Hooke's law. It's about Hooke's law. The wire has a cross-sectional area of 4.1 10 power negative 7 meter squared. This is the area, and is made of metal of Young modulus 1.7 10 power 11 Pascal. This is value of Young modulus. Assume that the cross-sectional area of the wire remains constant as the wire extends. A. State the law that describes the relationship between F and X as shown in figure 5.1. So the law, Hooke's law. B. The wire has extension of 0.48 mm. Determine stress. So stress equal force per unit area. So area is given 4.1 10 power negative 7. So we have to determine force. From extension 0.48, so extension 0.48 somewhere around here, we can determine force from graph. So force here. So here 36 Newton. 36 Newton divided by area equal to 8.78 10 power of 7 Pascal. B2 determine strain. Yang modulus equal to stress divided by strain. Yang modulus given 1.7 10 power 11, stress 8.78 10 power 7, and then you have to calculate strain. So strain equal to 5.16 10 power negative 4. C. The resistivity of the metal of the wire is 3.7 10 power negative 7 ohm meter. Determine the change in resistance of the wire when the extension X of the wire changes from X equal 0.48 mm to X equal 0.60 mm. Okay, now we have to determine the change in resistance. So formula, resistance equal to resistivity length divided by area. But because you want to calculate the change in resistance, so resistivity, you must calculate change in extension or change in length divided by area. Okay, so this is the change in length. So AX equal to 0.60 mm minus 0.48 mm. We have 0.42 mm. Substitute here. 3.7 10 power negative 7. Change in length 0.12 mm change to meter 10 power negative 3 divided by area 4.1 10 power negative 7. Okay, so change in resistor 1.08 10 power negative 4 ohm. 1.08 10 power negative 4 ohm. D. A force of greater than 45 Newton is now applied to the wire. Describe how it may be checked that the elastic limit of the wire has not been exceeded. Okay, so how to check elastic limit? So, if you want to check the elastic limit, when force is removed, wire can return to original length. So if wire can return to original length after force is removed, meaning elastic limit has not been exceeded. 6A, a battery of EMF 7.8 volt and internal resistance R is connected to a filament lamp as shown in figure 6.1. A total charge of 750 coulomb, this is charge, move through the battery in a time interval of 1500 seconds. This is time taken. During this time, the filament lamp dissipates 5.7 kilojoule of energy. This is energy. The EMF of the battery remains constant. 1. Explain in terms of energy and without a calculation why the potential difference across the lamp must be less than EMF of the battery. Okay, so we know that due to the internal resistance, some of energy will be lost due to the internal resistance. So, explain why. Because energy is dissipated in the internal resistance. Next, calculate current in the circuit. So, formula current equal to charge divided by time taken. Charge 750 coulomb, time taken 1500 seconds. So, answer 0.50 ampere. Calculate potential difference across the lamp. So, formula potential difference equal to work done divided by charge. Work done is energy, 5.7 kilojoule 10 power of 3 divided by charge 750 coulomb. So, potential difference is 7.6 volt. Number 3, determine the internal resistance of battery. Okay, so if you want to calculate internal resistance of the battery, here, this one apply the Kirchhoff's second law. So, Kirchhoff's second law state that sum of the EMF equal to sum of potential difference. EMF is 7.8 equal to potential difference across filament, VR, and potential difference across internal resistance, VR. So, internal resistance, again, sum of the EMF equal to sum of potential difference. 7.8 equal to potential difference across filament, IR, and potential difference across internal resistance. 7.8 because resistance in series. We have potential difference across lamp. We calculated 7.6 plus current 0.5 R. So R equal to 0.4 ohm. B1, a student is provided with 3 resistors of resistance 90 ohm, 45 ohm and 20 ohm. 1. Sketch a circuit diagram. Show how 2 of these 3 resistors may be connected together to give a combined resistance of 30 ohm between the terminals shown. Label the values of the resistance on your diagram. Okay, so we have to use 2 of these 3 resistors, but the total must be 30 ohm. So here you must connect parallel. 1 over R equal to 1 over 90 plus 1 over 45 ohm. 1 over R equal to 1 over 30 ohm. So R equal to 30 ohm. So we draw these 2 resistors connected parallel. Here is 45 ohm and then here is 90 ohm. Next, a potential divider circuit is produced by connecting the 3 resistors to a battery of EMF 9 volt and negligible internal resistance. The potential divider circuit provides an output potential difference V output of 3.6 volt. The circuit diagram is shown in figure 6.2. On figure 6.2, label the resistance for all 3 resistors and the potential difference V output. Okay, so we must know that the V output equal to 3.6 volt. Label all the resistance. Just now we arrange 2 resistors parallel. One is 45 ohm and another one 90 ohm. So meaning here the balance is 20 ohm. So if simplify circuit, become like this. Here 20 ohm and then here 30 ohm. Okay, where is the V output? So V output equal to 20 ohm divided by total times with the supply. This one you will get 3.6 volt. So the V output, okay, V output 3.6 across 20 ohm resistor. So this is the V output. (7a) A nucleus of an element X decay by emitting a beta positive particle to produce a nucleus of potassium and a neutrino. The decay is represented by this equation. 1. State the number represented by each of the following letters. So we have X, Q as decay K 3919, emit beta positive PR, and then neutrino 00. So we have to balance this equation. Beta positive R is positive 1 and P 0. So here R is positive 1 and P equal to 0. Q we have to total all. 39 plus 0 equal to Q. So 39. And then S, we have to total the proton number here. 19 plus 1. 19 plus 1, S equal to 20. 2. State the name of the interaction force that gives rise to beta positive decay. Okay, here is weak interaction force. B. A hadron is composed of 3 identical quarks and has a charge of positive 2e, where E is the elementary charge. Determine a possible type of the quarks and explain your answer. Okay, so this hadron have 3 identical quarks. So we have quarks 1, and then quarks 2, and then quarks 3, equal to 3 quarks of hadron. Okay, we quarks 1, for example, let's say we say X plus X plus X equal to positive 2e. So we have 3x equal to positive 2e, and then x positive 2e divided by 3. Okay, so this is the charge of this quarks positive 2e. Charge equal to positive 2e divided by 3, and then the type of this quark is up quark. Okay, now we done and settle this paper. Thanks for watching. Bye.